In this video, we will introduce the concept of instantaneous velocity. And to do so, we will start by looking at a motivating example. An object P falls 16 t squared feet in t seconds. What we would like to do is find its instantaneous velocity at t equals 2 seconds. That is to say, at the exact instance, when you're at t equals 2, what is the velocity of that falling object? Now, the motivation here is that calculating an instantaneous velocity, much like calculating the slope of a tangent line, seems like a difficult task. So what we are going to do is first look at an easier thing that we can calculate, the average velocity. Average velocity is defined to be the distance traveled over the time elapsed. And this is a very intuitive concept. For example, if it takes you 2 hours to travel 100 miles in your car, you would say that you had an average velocity of 50 miles per hour. So if we want to know what the instantaneous velocity is at t equals 2 seconds, what we can do is look at intervals around 2 and calculate the average velocity. So let's look at this first interval from 2 to 3. So we need a function that we're dealing with. Our function is going to be 16 t squared. How many feet the object has fallen in t seconds. If we want to know the average velocity on the interval from 2 to 3, we would need the distance traveled divided by the time elapsed. So how we can actually calculate this distance traveled will be f of 3 minus f of 2. So this would be the distance. And then we divide this by 3 minus 2. Because if you're going from 2 to 3 seconds, you take the larger 3 and subtract away 2. It took you 1 second. So this would be time. And for our function, if we go ahead and just plug in 3, put a minus sign, plug in 2, and divide by 1, what we are going to end up with is 80. So the average velocity on the interval from 2 to 3 is the number 80. And using a calculator and going ahead and filling in the rest of these values, I found on the interval from 2 to 2.1, it was 65.6. From 2 to 2.05, 64.8. 2 to 2.01, it was 64.16. And from 2 to 2.001, 64.016. And the big observation to make is as we shorten that interval around 2, we see that the average velocities appear to be approaching, we would say, the number 64. And for this reason, we are going to define 64 to be the instantaneous velocity. So once again, as we shorten that time interval, the average velocity is approaching 64 feet per second, and we will call that the instantaneous velocity at t equals 2. In general, the process that we've defined is that the limiting values of the average velocities will be the instantaneous velocity. So the instantaneous velocity at time t equals c is the limit as h approaches 0 of f of c plus h minus f of c over h. And to go back to that average velocity interpretation, what we have in the top, the f of c plus h minus f of c, is representing a distance traveled, and dividing by h is representing the time it takes to travel that distance. So let's go back to our original problem and use this limit to calculate the instantaneous. And a key observation to make before we do that is that the instantaneous velocity, looking at the equation that we have representing it, is nothing more than the slope of a tangent line. So the slope of the tangent line, instantaneous velocity, two very different sounding problems on face value, but we're actually calculating the same quantity. So an object P falls 16 t squared feet in t seconds. Find its instantaneous velocity at t equals 2. So the function we will use is 16t squared. It's the distance function, how far the object has traveled in t time units. So the instantaneous velocity at t equals 2 is the limit as h approaches 0 of f of 2 plus h minus f of 2 all divided by h. So just like our previous examples, the first thing to do is take care of the function evaluations. F of 2 plus h. Wherever there is a t in the function, we need to replace it with this quantity 2 plus h. So that would be 16 times 2 plus h quantity squared, and we're subtracting away f of 2, which is 16 times 4, or 64, all divided by h. Now, in order to evaluate this limit, we cannot simply plug in h equals 0. That makes the denominator undefined. But what we can do is expand algebraically in the numerator. 2 plus h quantity squared, 4 plus 4h plus h squared, and we are subtracting away 64 all over h. The 16 needs to distribute through the first term. 16 times 4 is 64. And we're also subtracting away 64. So we have two terms remaining in the top, and both of those terms are going to have an h in them. There's a 64h from when the 16 hits the 4h, and a 16h squared. So pull out the h in common in the top. And we're dividing by h. So we see that the h's cancel. What we are left with is the limit of a polynomial. So by the substitution property, the value of our limit is 64. And this number 64, as we previously saw, is the instantaneous velocity of this object at t equals 2 seconds. So since it's representing a physical quantity, we should give units. So this would be 64 feet per second. So a similar example here. A particle moves along a coordinate line, and s, which is its directed distance in centimeters from the origin, after t seconds is given by this function. So similar to the previous example, this function is representing how far the particle is from the origin after t seconds. And what we would like to do is find the instantaneous velocity of the particle after 3 seconds. So using our formula for instantaneous velocity, the velocity at t equals 3 seconds will be the limit as h approaches 0 of f of 3 plus h minus f of 3 all divided by h. Where in this problem, f of t is the function representing the distance of the object. So the square root of t plus 1. So our first step, once again, is to take care of the function composition. Whatever we plug in for t, we see where it appears in the function, and we're plugging in a 3 plus h for t. So that would be the square root of 3 plus h plus 1, and we are subtracting away f of 3, which is the square root of 4, or 2, and this is all divided by h. Simplifying just a smidge, underneath the square root we have a 1 plus 3, so that would be the square root of 4 plus h minus 2 over h. And once again, this is a very familiar type of limit. We cannot simply plug in h equals 0, but what we can do here is algebraically manipulate by multiplying by the conjugate over the conjugate. So we'll multiply by the square root of 4 plus h plus 2, divided by the square root of 4 plus h plus 2. And this works out very nicely because of the difference of squares formula. In the top, we're going to have the first term squared minus the second term squared. And in the bottom, we have the h, which was there, and the square root of 4 plus h plus 2, which we have multiplied it by. And we get all kinds of wonderful simplifications. 4 minus 4 goes away. H over h. That leaves us with simply a 1 on the top. So we have the limit as h goes to 0 of 1, divided by the square root of 4 plus h plus 2. And at this point, we cannot use, say, the substitution property because it's not a polynomial or rational function because of the square root. But what we've seen through many examples at this point is that we can break it up in terms of the limit of the top over the limit of the bottom. The limit in the bottom can be broken up between both the terms. And in the first term, the limit can go inside the square root, and we'll end up by the substitution property just plugging in h equals 0. So the value of this limit is going to be 1 over the square root of 4 plus 2, which is 1/4. And the units to go here is we're measuring distance in centimeter and time in seconds. So the instantaneous velocity is 1/4 centimeters per second.